Okay, let's get started. So anyway, congrats to everyone. We were able to get through the first 1/3 of the course. So this lecture, it's basically split, half lecture today, half lecture tomorrow, will be the last lecture of the large block that is mostly devoted to chemistry. And then we will move to some things that are, let's say, more biological by nature. So a bit less chemistry, a bit more biology. And that's good. And I hope you have seen that we will have some sort of midterm. So if you check the problems, there are some additional sections. So section with midterm problems and section with midterm essay. Good. That's good, but enough with that. Let's get to something more interesting. First of all, today's lecture is devoted to, let's say, kinetics of chemical reactions. And to fully appreciate everything that we have there, well, basically you will probably need at least 2 courses from physical department, like statistical mechanics and thermodynamics. So we will today just dash through some general ideas, and that's it. But I want you to know that there is something more in the background, and if you feel interested, please check books on these 2 topics in physics, and there is much to learn, I guess. So combined together, they are really powerful. So here is a list of whatever we can achieve by combining these 2 disciplines. Here are let's say some achievements of statistical mechanics. So what I want you to know about statistical mechanics. First of all, it knows about the molecular composition of matter. It may be classical, it may be quantum, but anyway, it knows about this composition. Second, it operates with microstates. So we have different microstates in the system. So one microstate is, let's say, how you have positioned all your molecules in the system, and you have given them some sort of velocities, so on and so forth. This is one microstate. If you move one of the molecules, you will get another microstate. And that's really huge. So it uses probability distributions to cope with huge number of equations of motion. You know that in classical mechanics we cannot solve equations for 3 bodies. So here we have, I don't know, 10 to the 23rd bodies, so we should use some different mathematical apparatus. And we can calculate some measurable parameters as statistical or quantum mechanical averages. Here are some results, so don't be afraid. I will not expect you to remember all the things, but they are pretty useful. So here is Maxwell-Boltzmann distribution that basically tells us how many molecules may have certain velocity, and so on and so forth. And you can use that to calculate, for example, how many molecules are able to undergo certain chemical reaction because they have enough kinetic energy to get into that reaction. Here are a few equations for Brownian motions. That was one of the first evidences of the molecular composition of the matter, so they matter as well. And of course there are pretty large amount of other results. So for example, blackbody radiation, Fermi Dirac statistics, and so on and so forth. On the other hand, thermodynamics is largely phenomenological branch of science that ignores the molecular composition of matter. So it's just phenomenology. So you introduce certain parameters and you say that they evolve according to certain laws of thermodynamics. As all physical laws, we let's say obtained them experimentally, so we have performed a number of experiments, and then we got the idea that in all these experiments certain statement is true, and we call this statement a law. So here are 3 laws of the thermodynamics. So Vero's law tells you that temperature is a state variable. And the first law is basically law of conservation of energy, while the second law tells you that entropy always grows. We will get to that in a moment. And third law tells you that basically there if temperature is 0, I mean absolute 0, so it's not 0 by Celsius but by Kelvin, so it's absolute 0, all processes cease and entropy of the system approaches a minimal value. And this area has, let's say, certain concepts. If in case of statistical mechanics we operated with microstates, then here we operate with macrostates, so the state that describes the whole system. And here we use some functions, aka potential, so quantities that depend on the macrostate and independent on the path. So here they are. We will operate today with, let's say, a few of them, so it's probably worth knowing. So there are such things like state variables or state functions. These are macro coordinates of the system, or let's say properties that do not depend on the path. What do I mean by path? So you have certain parameters of the system. Well, the simplest, for example, pressure, temperature, volume, and so on. You are changing somehow temperature or pressure or volume or whatever, so you are performing certain changes. You perform these changes in time, so time goes and you change something. If some quantity is a state variable, that means that independently how you change that all over the time, you are interested only in the beginning state and in the end state of the system. So quite an analogy, for example, potential energy. So you remember that potential energy is basically mgh. So if I am calculating potential energy for some mass, being, I don't know, on the second floor, it doesn't really matter how did I get this mass into the second floor. Did I just take it there from the first floor? Did it get there from the third floor? So I first go to the third floor, then I return to the second floor, and so on. It doesn't really matter. So this is a quite an analogy of this case. And the thing is that these all these variables, they are independent on that path, on the history of the system that is evolving. And that will be crucial for us because we will solve some problems just in a moment, and we will use this property that we do not need to know what happened to the system between the starting point and the end point. Here is some notions that heat is not a state function, so that's okay. But here are pretty many variables that are. And of course, we don't need all of them, we don't need to consider all of them. If a homogeneous system in thermodynamic equilibrium, you can pick any two of them, and the rest will be just functions of these two picked variables. Which of them to pick, that depends on the problem that we are solving. A few more notions. The property is called extensive if it is proportional to the side of the homogeneous system. That means that, for example, enthalpy. So if we have some enthalpy of a 1 mole of gas, for example, if we add 1 mole of gas in the same state to get 2 moles, we will basically need to multiply that by 2. Not all properties are extensive, but some are. So here is a list, for example. So volume, internal energy, entropy, so on and so forth. You may notice sometime these sort of circles. What it means that this parameter was measured under standard conditions. So standard conditions, so it goes not only for Gibbs free energy but for all of them. It's basically temperature 25 degrees C or 298 Kelvin, pressure of 1 atmosphere, it's something around 100 kilopascal, and with 1 molar concentration of all aqueous solutions. So that's what we have. In some cases, you may see additional this sort of prime sign. So you have circle and you have this thing. That may additionally tell you that we are working at pH equals 7. It's not like something special, but you will often see these designations in different books, so I want you to know them beforehand, so you will be not confused what is this circle or something other. So it's just measured at some at some conditions. Here are, let's say, 3 thermodynamic properties that we will use at most. The Gibbs free energy. We write here delta. Here is a tricky question for you. How do you think, why we so suddenly jump to deltas? I remind you that all these things, so G, H, and S, are all state variables. So how do you think, why are we interested in some sort of differences? Oh, I see chat. Yes. Delta denotes change. Yes, that's difference. Difference between between final and initial state of the system. So we can write delta G like G, I don't know, final minus G initial. Well, in some sense, yeah. You see, these are state variables. This means they do not depend on the history of the system, which means that only their differences have certain, let's say, physical sense. So they do not depend on how the system got from one place to another. Let's I remind you for let's say potential energy. So I have some levels with potential energy. They are going, I don't know, infinitely down, infinitely up. If I have system here and I move it, I don't know, I move it first here, then I don't know, here, then here, and so on. The value of G that I get here will not depend on this path. I could immediately take it to here and that will be pretty the same. Which means that if I calculate difference between these states, it is pretty meaningful. Because you are like throwing away all the history of the system and just considering the difference between initial and final states, and you just throw away all the rest. So we will often operate with this sort of deltas just because these are state variables. In case of non-state variables, you can't do that meaningful. So it won't give you the information you want. For example, consider the length of the path. So once again, I'm trying to move system around through levels, but now I am considering the length of the path. And of course, getting system from this level to this level directly and getting it first here, then here, then here gives you pretty different lengths of the path. So here I have moved through, I don't know how many, 1, 2, 3, 4, then 5, thick 7, then 8 floors. So the length is 8. And here I have moved through 2 floors. So this is not a state variable, and you cannot, well, delta will tell you nothing. But if you consider potential energy, that will tell you, because potential energy does not depend on all these things. It depends only on the difference between these two states. Okay, let's move further. I guess maybe we'll get some more insights as we go. Okay, so the first state variable, pretty interesting for us, is the enthalpy. So here it is, designated with H. It is said that this is work that will be required to make room for the system if the pressure of the environment remained constant. So you may think of it like, I don't know, you have here some sort of environment, it has certain pressure, and I am trying to squeeze in here my system. So I need to, let's say, push away the gas or the liquid, whatever I have here, and if the pressure remains constant, this will be the requirement for the work. So how hard is it to put this system into there? Here are certain thermodynamical relations. For example, if the pressure is constant, so dP equals 0, the increase in enthalpy of the system is equal to the heat added. So here is the first law of the thermodynamic, and just few equations to show that. Well, once again, I don't expect you to operate with all that differentials, so I just want you to know that we can prove certain statements, and here is one of them that we may use in the future. Okay, why is enthalpy interesting for us, let's say, from the chemical point of view? So from the physical point of view, okay, that's more or less, I guess, clear. But what about chemistry? So in chemistry, by the difference in the enthalpy, we may calculate whether reaction is endothermic or it is exothermic. So for the endothermic reaction, we will get delta H lower than 0. So once again, we are taking this delta. So we are forgetting about all the history of the movement of the system, and we are interested only in the state we start and state we end. If we take enthalpy of the end state minus enthalpy of the starting state, we get delta H. If this delta H is less than 0, we get endothermic reaction. So this reaction will need some supply of heat from the environment. If we get something greater than 0, this is an exothermic reaction, and we probably will generate some heat during the reaction. Here are two examples. So here you see barium OH2 with NH4SCN, and this is an endothermic reaction. So you see that the temperature is pretty low, so it's something like minus 0.09 degrees C, so it's around 0. Or we have an extremely exothermic reaction, that's iron oxide with the aluminum. Well, I guess here is some sort of error. I guess it's just with aluminum, because this is the classic thermite reaction. So aluminum is being oxidized while iron gives its oxygen to the aluminum, and we get a lot of heat in the process of the reaction. Okay. And of course, since this enthalpy is so useful, we might get enthalpies of different processes, or let's say some uh, sub-processes in the system, and we may be interested in that sort of processes or sub-processes. So what do I mean by that? For example, the enthalpy of, I don't know, vaporization. So some chemical reaction goes, and then one of the chemicals vaporizes. So we may be interested in the part of vaporization, or sublimation, or enthalpy of solution. So I'm taking some chemical and I'm dissolving it in, I don't know, in water, for example. So that all may be somehow measured, and you may find some tables with the typical enthalpies for different processes, and use that as you need when you calculate something. Here is one more example of, well, you will tell me what kind of reaction is that. Is it endothermic or exothermic? So let's look at the experiment and you will probably tell me. So here he's just dropping some water. So it's just water, and it will basically not take some part in the reaction, but you will see why do we need that. Here you see the reaction performed. So once again you see all these reactants. I will not go through that, but let's look what happens. So mixing, mixing, mixing. And now you see what happened. Who will tell me what exactly was that, and was this reaction endothermic or exothermic or whatever? Endothermic, yes, absolutely correct. It's endothermic. So it, let's say, it takes heat from the environment, and it takes so much heat that the water that he used just freezed, and that's why we see that we cannot take apart now this wooden block and this I don't know what that beaker, some sort of beaker, for example. Good. One more thing to notice is Hess's law, and these we will probably need somewhere, or at least some general ideas. So once again, the enthalpy is the state variable. So it does not matter how the system got from the initial state to the final state. It sounds pretty abstract, but you can, let's say, translate that in some sort of more chemical language. In this case, what do we tell? So if we have some chemical reaction, so well, that's all that chemicals mixed in a beaker, for example. That's an example of a system. When reaction proceeds, this system is basically traveling from one state, when we have our initial chemicals mixed in that beaker, to the final states where we have some sort of results of our reaction. So we have some products. Okay, and the fact that the enthalpy does not depend on that path of the system means that we can calculate difference in the enthalpy only knowing where did we start, so what were the initial reactants that we have mixed into that beaker, and what is the final state. So after whatever happened to that beaker, so it doesn't really matter. When we are in the final state, we know the enthalpy and we can calculate that difference. It is meaningful. So if reaction is carried out in a series of steps, delta H for the overall reaction equals the sum of the enthalpy changes for the individual steps. So that's why we are so interested in that deltas. We can combine the deltas to get the final delta. The overall enthalpy change for the process is independent of the number of steps and independent of the path. And this law is the consequence of the fact that enthalpy is a state function. So basically, what I've told you. Let's look at some sort of example. So here is an example. I am trying to I'm looking at the equation of combustion of the methane with the oxygen. So of course we expect some CO2 gas and water to be formed. Well, we can see this as two steps reaction. So first, everything combusts, gives you CO2 and water, but this water is gaseous. Then this water can transform to the liquid form. And these two reactions can combine to give us the final reaction. So we have combustion reaction that gives us CO2 gas and liquid water. So I am sort of considering condensation of water as a separate step. I know the delta H for this step, and I know the delta H for combustion of the methane and giving me two gases. If I add all these reactions together, so look at that, we are just adding them like, I don't know, like in algebra course. So here is CH4, here it is. So here is 2O2, here it is. Here is 2H2O. Once again, H2O liquid, yes. H2O gaseous, here it is. CO2, here it is. Then, as in the same way as we do that in some sort of courses of algebra, we can remove something from the both sides of the equation. So here it's what? So in these equations, in this equation, what do you see on the both sides of the arrow that can be basically removed, that is the same? Think of it as sort of, I don't know, algebraic equation. H2O gaseous. Yes, absolutely correct. So this thing and this thing may be removed. And here is the final equation that we get. And if I add these two deltas, I get the delta H for this final equation. Let's take a look at one more example. So here is the formation of the CO2 from its elements, and we can think of it well in two different, let's say from two different sides. So you can think of it as a formation of CO2 directly. So here we have carbon dioxide gaseous just formed from the carbon and oxygen, and we have certain delta H. But we can think, let's say, it could happen that first we generated carbon monoxide, so here it is, and then this carbon monoxide combusts and we get carbon dioxide. And once again, we have some delta H for this process for generating carbon monoxide, and we have delta H for generating carbon dioxide from carbon monoxide. Now we remember that all these deltas do not depend on the path that the system has taken. So it doesn't really matter whether we created this carbon dioxide directly or through some intermediate step. And now we are trying to calculate the difference between these states. So if I want this delta H, I need some sort of H for, I don't know, CO2 minus HC plus O2, let's call it just HC. In this case, I have this delta H, that is H of CO2 minus H of CO, and I have this one that is basically H of CO minus H of C. And now do you see how do I need to combine these things to get this thing, to get what I want? What should I do?
Temperature.
Look at them. So we have one process that goes in one step, and I take difference between final state and initial state. So here's what I have: HCO2 minus HC. So I call this state HC. This is called HCO2. This is called HCO. And I want this difference. How do I create it if I have this difference and this difference? Yes, to add them. Absolutely correct. I just need to add them. When I add these two quantities, my HCO is going away if I add them, and I get what I want. And the property that I can add them and get the final result is basically based on the fact that enthalpy is a state variable. So everything starts there in thermodynamics with the fact that this is a state variable, and then we get to these things. So we can do calculation of difference of enthalpies between different states. If we don't know this number directly, we can use some intermediate steps. And it doesn't matter whether these reactions are feasible or whether they occur in practice or not. It does not matter. So we only need to be able somehow to get from here to here. Here is some sort of example with different enthalpies, but I don't think we'll get deeply into that. I just want you to show that here are basically two states, so molecule without any double bonds and some sort of alkane with one double bond. And depending where this double bond is, we can calculate difference in enthalpies and then use that. Of course, they may have some little bit deeper meaning. For example, these ones, basically there is effect of electron, a little bit electron releasing effect of alkyl groups. That the first effect, and the second effect is some sort of steric hindrance. So this becomes more stable, and this becomes even more stable because you have no steric hindrance and you have double bonds in the middle. But okay. And here's an example. I want you to look more carefully because we have the pretty similar problem for the homework. So let's try to do this one together to get, let's say, some ideas of what is happening. So what do we have here? I want to get the enthalpy of these reaction. Well, delta H, let's say, difference in enthalpies from the reactants and the products for these reactions. But suppose I cannot find it in any of the tables. It seems I can still recover this quantity if I find some different reactions that involve these sort of reactants and products, and I will construct some hypothetical, so it should not exist in practice, it doesn't really matter, some hypothetical path that will take me from my initial state to my final state. And suppose our table gives us these three reactions, of course with their delta H's. So here's what we have. Now what we want to do, we need to construct this equation out of these three. What can we do? So what are our instruments? We can operate with them in a pretty similar fashion as we do with, I don't know, some elementary algebraic equations. So you can multiply them by some sort of number, for example, multiply that by 2. All quotients get multiplied by 2. Now, delta H gets multiplied by 2 as well, because this is an extensive property. So the more moles you have, the larger this quantity gets. So it is scaled with the number of moles. You can add them as we did in the previous example. So you can add them and then you can cancel out some sort of reactants that you have on the both sides of the arrow. You can do that as well. And what else you can do? You can reverse this arrow, but it goes with the cost of getting here a minus sign. So I can take any of the equation, I can reverse the arrow, but I will need to multiply by -1 the delta H that I have. Well, that's pretty reasonable, because delta H, that's the final state minus the initial state. If for some reason I reverse the reaction, my final state becomes my initial state, and my initial state becomes my final state. So they swap places, and since we were subtracting them, we need somehow to compensate for that minus sign. Now let's try and do something with these sort of equations. So we need to construct this one from these three. Okay, so what do we do? We can take, let's say we see that we have here chlorine fluoride, and we have chlorine fluoride here. So we may start with this equation, but we don't need these two. So let's divide everything by 2. So here it is. I have divided by 2, so I have chlorine fluoride here. I have 1/2 of O2 here. I have 1/2 here and 1/2 here. Now, what should happen to delta H? Who will tell me? So I have multiplied here by 1/2. Yes, it will be divided by 2. Absolutely correct. So I need to divide these by 2. And basically I will have something 100 and something. So here it is, 102.8 kilojoules. Great. So now I see that I have here some sort of oxygen, but I don't need it in this reaction. So I will need some other reaction to compensate for that oxygen. And here is only one place where we have oxygen, so this reaction. So what I should do, I should first reverse it. So I need to change the direction of the arrow. And the second thing, I have 1/2 here, and I have nothing here. So I need to multiply that by 1/2. Now what will happen to the delta H? I have reversed the arrow and I have multiplied by 1/2.
-2.
So I should take minus sign. I will get plus 49 and
Divide.
yes, absolutely correct. So I should divide that by 2. And we have in our chat, of course, correct answer. So multiply by minus 1/2. Absolutely correct. And here is what we get. So you see we had minus here, now we have plus, and we have 49, something near 50, and we get something near 25 here. So pretty okay. Good. What else? So now we will be able to do something with all these things. Now we need to compensate for, let's say, for some more things. Let's take this equation. So now I have oxygen here, I have oxygen here. They combine into one oxygen. I have, let's take this, chlorine fluoride here and chlorine fluoride in my initial equation. That's really good because I need it to in the final answer. I have fluorine here and fluorine here. That's perfect. That's what I want. Now I don't have chlorine fluoride 3. I don't have it anywhere. And I need, on the right side, I don't have oxygen to compensate for this thing. Well, and to somehow compensate all these parts. And it turns out I can do that. If I take this equation, I should once again, I guess, invert the arrow. And probably that's all. So if I just invert the arrow, what happens to the delta H? Multiplied by -1. Yes, absolutely correct. So it picks up a minus sign. So here we have it. And here is our equation. Now let's try to add them together and look what is left and basically what we have. So 1/2 O2, 1/2 O2 gives me a full O2. And I have O2 here. So from different sides of the arrow. So I can cancel them out. Here we have it. What else do I have so interesting here? I have three halves of OF2, and I have 1/2 OF2 here and 2 halves of OF2 here. So they are basically cancelled out. Okay, anything else? One half of this chemical and 1/2 of this chemical. They are cancelled out. Now what is left? Chlorine fluoride, fluorine, and chlorine fluoride 3. So here we have them, which is equal to the initial equation. So we know that these 3 equations combined will give me this first equation. So if I add all these delta H, I should get delta H for this equation. Is it more or less clear what have we done? you'll get a more simple problem for the homework, so it will be much easier to find how to combine the equations, but I want you at least to think on the, let's say, conceptual level. So are there any questions regarding what we have done? Okay, no questions, good. So basically this is a technique that may help you to calculate delta H for any equation that you want, well, basing on some sort of values from the tables. So there are tables on the internet, you can take these sort of values from there, and of course if your reaction is not in some of the tables, you can combine whatever you have there to get delta H for your equation. That's good. Entropy, one more state function that's basically a measure for the number of possible microscopic arrangements or microstates, so of individual atoms and molecules of a system that comply with the macroscopic condition of the system. This is basically a statistical mechanical definition. So thermodynamics will give you a little bit different definition, but I really like this one more. It's more, let's say, insightful. So in statistical mechanics, you will have this sort of formula for the entropy, where this W is basically the number of microstates. The question of how do we calculate the number of microstates, well, depends on the physical system. In some cases it's quite tricky, and you can basically make a good physical article out of calculating the number of states for certain systems. Here is the Boltzmann constant, K, sometimes written KB. So you will probably see somewhere this with this sort of subscript. Okay, and here is a bit more thermodynamical definition, but that works only for reversible processes. So if you can reverse the process, this will be okay. If the process is not reversible, you will have sign greater here, so it's always greater than this quantity. And here you see some sort of example of increasing entropy. Sometimes people are even defining entropy as the sort of measure for, let's say, chaos in the system, but it's not, let's say, quite physical, so we better stick to the more physical definition through microstates. Of course, the more microstates you have, probably the more disordered your system will look to you, just because you have much more abilities for this system to wander around. But anyway, and here are examples for increasing entropy. So here is ice, and you don't have so many microstates because all your molecules are basically sitting in one place and they almost cannot move around, so just a little bit. In liquid water they have much more ability to move around, and here you have a larger number of the microstates. And if you get to the water vapor, it has even more entropy because these molecules are just unrestricted and they can go all over the place, and you have much more microstates. And here is an example when you have that in chemistry. So this is a chemical reaction when you have in gaseous phase two gases that are combined into one gas, and that basically makes the number of microstates smaller. I guess we'll see some examples of that. Here is an example of this sort of calculation, so I will not go really deep into that, just to show you that this is possible to calculate. So once again, entropy is the state variable, so you can so it is meaningful to calculate these sort of deltas, like entropies of products minus entropies of reactants, and you will have even these sort of tables on the internet when they provide you with some sort of entropies. This circle, it's I remind you, that's for so-called standard conditions. So the temperature is 25 degrees C, pressure 1 atmosphere, so on and so forth. And here is an example when you combine nitrogen gas with hydrogen gas and you get ammonia, this sort of NH3. And if we calculate difference in the entropy, we can use this sort of table and we get some value out of it. And why do we may want to know this value? Because if we consider the entropy of the universe, it means the system plus the surroundings, we should get a result that is either 0 or greater than 0. So if it is 0, the process is reversible. So it may go one direction, it may as well go the other direction. And if it is greater than 0, it is irreversible, because entropy should grow up due to the second law of thermodynamics. Here is an example of ice melting when the system gets some energy from the surrounding environment, and here is an example that shows you that this is an irreversible process, because the difference of the entropy of the universe is greater than 0. Gibbs free energy. We will use that a lot, because that basically describes some sort of how the reaction is going. So here is the formula. This is H minus Ts. T is temperature, S is entropy. So we have seen them all in the previous slides. So the change in free energy for a process, delta G, it equals the maximum useful work that can be done by the system on its surroundings in a spontaneous process during constant temperature and pressure. What's interesting for us, the sign of G tells us whether the reaction is spontaneous at constant pressure and temperature. Well, basically sign of delta G. So here we have equation for delta G, some small proof, whatever. So if delta G is less than 0, the reaction is spontaneous in the forward direction. So you have some reactants, you have some products. If you calculate delta G, that will tell you whether reaction has tendency to go in the forward direction. So your initial reactants, your substrate, will transform in the product if you wait long enough. Or if delta G is greater than 0, this reaction will not want to be spontaneous. So if you have a mixture of your reactants and your products, it will turn out that your products will degrade to your initial reactants if delta G is greater than 0. If delta G is equal to 0, the reaction is at equilibrium. So regarding equilibrium, we will talk about that. Here is one more small proof. Okay, I don't think you should get into that. What I want you to show is basically this equation. Mole means per 1 mole, so this is a mole. This is molar, and here is Q that tells you, let's say it's a coefficient for this sort of reaction. Let me show you the other slide. I guess, yeah. We will probably use this sort of formulae somewhere. So reaction quotient Q, you can calculate that from so-called activities. These activities, they are mostly in the problems we will consider, that will be either concentrations in the solution or partial pressures for gases that are basically proportional to the concentrations. So most cases that works fine, unless you are considering something really strange. That's one thing. The other thing, when reaction is in equilibrium, I remind you that delta G should be equal to 0, and in this case we call the reaction quotient, we call equilibrium constant, and we use letter K. So here are just few results you get from this formula. Just moving around, nothing, let's say, complicated. But what's interesting for us, if we have reaction in certain state, we can calculate this sort of reaction quotient Q. If Q is less than K, then reaction has tendency to move to the right. If it is greater than K, then reaction will move to the left. If it is equal, reaction is in equilibrium. So here's an example. So all reactions, they tend to go to some sort of minimum of this G, of the Gibbs free energy. And if Q is less than K, then reaction is spontaneous this way and tends to go here. If it is greater than K, then it is spontaneous in this direction and it tends to go here once again. Here's an example. If we change this Q, the reaction proceeds, if it is less than K, it proceeds to form more products. As it goes, we have these Q and K, they become equal, so reaction is equilibrium. Or if we have Q greater than K, reaction proceeds to form more reactants, and once again you return to the state of the equilibrium. Regarding equilibrium, so this is so-called thermodynamic equilibrium. It's a state of a system in which all macroscopic flows of energy and matter, seeds, and all types of equilibrium, mechanical, thermal, chemical, are satisfied. So that's thermodynamic equilibrium. And all macro states, they become constant. Dynamic equilibrium means that we have the same macro states, but we have changing microstates. What does it mean? For example, I have this sort of beaker. It's a closed beaker, and I have some liquid in there. This liquid, it may evaporate or it may condense. If I wait long enough, this system will be in equilibrium. It doesn't mean that only the same molecules are being in liquid phase or in gaseous phase. So some molecules are always moving from the liquid to the gas and from the gas to the liquid. But if I measure any of the macroscopic parameters, I don't know, pressure, volume of the liquid, volume of the gas, temperature, whatever, they are all constant. So this is an example of an equilibrium. So this is a closed system, and it is in the thermodynamic equilibrium. If I open this beaker, so I remove this sort of watch glass or whatever it is, the system will be no more in the equilibrium, and probably the liquid will fully evaporate. So why not? The same thing goes about chemical reactions. So if we have chemical reactions that go, let's say one goes in one direction and the other goes in another direction. We had that in case when we considered acids and bases. So I guess you remember we had acid AH. It could transform into conjugated base A and H+. But this reaction could go another direction as well. So we have a proton, we have conjugated base, and we can combine them. And in the case of equilibrium, when it is reached, the reaction rate of forward and backward reactions, they become equal. So if they are equal, it looks like nothing is changing. We have the same amount of AH, we have the same amount of protons, and so on and so forth. And here, if you look at the concentrations have stabilized. So they are stable. If you measure them, you will get the same exact number. But something is changing. So molecules are still undergoing reaction, but we just don't see that on the macroscopic level. And here I guess I have a video for you that in some sort of mechanistic way tries to represent you how that dynamic equilibrium looks like. So these two spoons, they represent like two reactions. So one is the forward reaction, the other is the backward reaction. And these two containers, they sort of represent you a pool of initial reactants and the final products. But since the reaction is reversible, our products may degrade to our initial components, while our initial components may react and get you some products. And here is what happens. So how the dynamic equilibrium looks like and how it is achieved. So you remember, I hope, that formulae that we wrote for our reactions, and they involved basically the concentrations of the reactants. So you see this container is, let's say, more empty. You cannot scoop a lot of liquid with the spoon. So it's basically waiting until you get liquid to some level. And the same is true for this initial container. So what you see is basically a dynamic equilibrium. So something is happening. Reactants are transforming to final products. Products are degrading to initial reactants. But if you look at that long enough, you understand that at some point an equilibrium is achieved, and as much liquid you get from left to right, the same amount you get from right to left. So the same thing happens to your reactants. So the same amount that is moving from reactants to products, the same amount of products is degrading to your initial reactants. So that's what we have. Okay. Few more things to mention. Everything goes with this sort of equation, and with our knowledge that the sign of the delta G tells you about spontaneity of the reaction. So what's interesting here? If you calculate delta H and delta S, they will have some signs. Let's say minus and plus. If you calculate this delta G, it will always have minus sign, independent on the temperature. Always will have minus sign. Why? Because T, that's temperature in Kelvin, so this is always a positive number. It is multiplied by delta S, that is positive in this case. So you always get T delta S positive. With minus, it will be always negative. And you have delta H that is negative, so together is always negative. What is negative? Reaction is spontaneous in the forward direction. So independent on the temperature, you get reaction that is spontaneous, whatever is the temperature. And here's an example. So O3 transforms into O2. Okay, what happens if delta H is positive while delta S is negative? What does it mean? Negative delta S multiplied by positive temperature gives you a negative number. With minus sign, that will give you a positive number. And now you combine that into delta G and you always get positive number. Which means that this reaction is non-spontaneous, whatever is the temperature. So you change the temperature, this reaction is, let's say, spontaneous in the backward direction. So not the forward, but backward. And here is basically the same example, but I have just swapped places, reactants and products. Now the more interesting cases. For example, we have delta H minus and delta S minus. In this case, you multiply that by temperature, you still get negative number. But with minus sign, it becomes positive. So now here, in this equation, this is basically a tug of war. So the sign of the delta G will depend whether delta H is so negative that everything goes down to the minus, or T delta S is so positive that it gets you up. And now here is a tricky question for you. So suppose at some temperature, I know at room temperature, these delta H dominated. So I had minus sign. So delta G was minus at room temperature for these cases. What does it mean? Is the reaction spontaneous in the forward direction or not? So delta G less than 0. What does it mean? Spontaneous, yes, absolutely correct. So it is spontaneous in this case. Now suppose that I am increasing the temperature. What may happen to the delta G? So I'm considering these both being minus, and I have delta H minus T delta S. So this thing is minus, this thing is plus. And now I'm trying to increase the temperature. What will eventually happen? Yes, delta G goes up, absolutely correct. It will become greater than 0. Yes. And at the moment it becomes greater than 0, this reaction starts being non-spontaneous. So it will be spontaneous in the backward direction. And similar logic may be applied to this case when we have two pluses. The same thing. So basically, if you calculate these parameters, like delta H, delta S for your reaction, you may not only tell is the reaction spontaneous or not, you can also tell what should you do with the temperature. And is it meaningful to change the temperature? So maybe whatever you change the temperature, it will not help you to do something with the reaction. Or you may calculate the temperature you should have to make your reaction spontaneous in the forward or in the backward direction. So depending on what do you want. Okay, here is one more example. This is a Haber process, and we see how delta H changes with the temperature. So, okay. T is in Kelvin. Yeah, I said that few times, so in case you missed this point, please, T is always in Kelvin. That's really, really crucial, because this is the only scale that has true zero. So zero in kelvins is meaningful, because that's really the temperature that has some sort of physical meaning. That's the case where all your thermodynamical processes achieve the lowest possible entropy. So that's really a crucial thing. Please note that. So you need kelvins always. Good. One more thing. I guess we have 20 minutes. So so-called Le Chatelier principle. This is the principle that tells you that if the equilibrium of a system is disturbed by a change in one or more of the determining factors, let's say temperature, pressure, concentration, whatever, the system tends to adjust itself to a new equilibrium by counteracting as far as possible the effect of the change. That was discovered by extending some sort of reasoning from the Van Hoff's relation. I will not go through this derivation, we have no time, and probably you don't need that. But here is a nice illustration of the principle. So if stress in form of a homework is applied to the system will adjust itself by just burning everything down and to relieve the stress. Okay, what about, let's say, more well-behaving systems that will not burn everything down? Concentration. Let's check what happens when we change concentration in this system. So adding or removing reactant or product may influence the equilibrium. So here are a few nice images. We have some initial equilibrium. We add one of the substances we had, and we achieve a new equilibrium. So here you see that we have a bit more of a product because we added a little bit more of one of the reactants. And here is some plot that shows you some initial equilibrium that we have in the system. So we have these three gases. They are in the equilibrium, so some H2 plus N2 are transformed into NH3. Some NH3 is degraded back to N2 and H2, but basically concentrations stay the same. We add a little bit more hydrogen, and after some time, so system is disturbed, something is happening, but time passes, new equilibrium is achieved, and you see that it is different from the initial equilibrium, and it basically changed so that it tries to compensate the change that we had. So we added more H2, system did something to somehow deplete this H2 and to make its concentration a bit lower. Very often used, well, probably the best case scenario, you can shift the equilibrium of your reaction by removing the reactants. So here is some sort of complicated scheme, but all in all that tells you, so if we remove products from the reaction, we force system to create new products because it wants to be in the equilibrium, and that is probably best case scenario. So if you come up with some sort of new chemical and some way to synthesize that chemical, if you will be able to extract products from your, I don't know, reaction flask or where do you do that, that will be perfect, because the equilibrium will always force the system to create for you more and more product while you are extracting that product. So pretty good. Not always feasible, not always possible, but if you can do that, I guess it's pretty nice. Temperature and the Le Chatelier principle. So if a temperature of a system in equilibrium is increased, the system reacts as if we added a reactant to an endothermic reaction or a product to an exothermic reaction, and the equilibrium shifts in the direction that consumes the excess reactant. So here is an example. So we have endothermic reaction. Increasing temperature, reaction shift to the right. Decreasing temperature, reaction shifts to the left. Well, pretty reasonable. So endothermic reaction gets some energy from the surrounding. We have added more energy, so this energy can be now used to create more products. Exothermic, basically the same logic in the reverse direction. Here is an example of an endothermic reaction. So some sort of cobalt salts and chlorine. So whatever is happening, but the interesting thing that you can see that by color changing. So you change the temperature of the surrounding environment, and depending on that temperature, the equilibrium shifts to the left or shifts to the right. The reaction is endothermic, that you know by the delta H. So endothermic, if you add more heat to that, it tends to go to the right. So in the hot water, you will get more, let's say, bluish tint, because you get more of the cobalt chloride that is blue. If you instead use some cold water, so you are trying to cool your solution, your reaction equilibrium shifts to the left, and you get more of the pink color, because this is this sort of chemical. So some cobalt basically dissolved in water. Good. Here is an example from our lecture 3. So we had this sort of equation, that's auto ionization of water, and here you see that the equilibrium shifts depending on the temperature. Some more effects are involved, but anyway. Here is one more example. I really like this one. So here we have a chemical equilibrium. These are NO2 and N2O4, and we have two beakers with water, so hot water and cold water. Let's look what happens when we put that into any of those. Okay, do you see how the color changes?
Yes, you see it. It becomes darker.
Yes, it becomes darker in the hot water, and it becomes more transparent in the cold water. So let's check once again. So you are basically seeing how the equilibrium is shifted with respect to the temperature. So you are adding some temperature, you are, well, adding temperature sounds dubious. So you are adding some heat to the system, you are placing that in the conditions with higher temperature, and you get your equilibrium shifted to the left or to the right. So here you have shifted to the left, here you will have shifted to the right, and that can be seen basically by the color of whatever you have in here. So that mixture of gases, you can see how the color is changed. So this reaction from left to right is exothermic. So if it is exothermic, if you put that into cold water, it will tend to shift to the right, because it's exothermic, so it wants to reject some heat, and you are helping it to reject that heat by placing your ampule in the cold water. In the reverse direction, the reaction will be, of course, endothermic, so it will want to acquire some heat, and you will help it by placing this sort of ampule in the hot water. So I hope this logic is more or less understandable. And of course, you may see these delta H's. They are, it's not, let's say, random fact that they are equal by the absolute value but have different signs, because we have just solved a problem with you where I have reversed the direction of the reaction, and we have put the minus sign for the delta H. Good. Pressure can be used as well to manipulate the equilibrium for the reaction. And you see that if we have some reaction that, for example, creates from two molecules one molecule, if you increase the pressure, it will tend to transform these two molecules into one molecule, so to take, let's say, less volume per one molecule. If you increase the volume, that will go the other direction. Good. I guess few words about transition states and we will be almost there. So I showed you a lot of different thermodynamic parameters. We saw how do they work, so on and so forth. And now I want to show you some neat plots with the Gibbs free energy, the delta G, because they have certain meaning and some sort of may help to explain some sort of reactions and how they go. Few keywords for you. A transition state represents an energy maximum. Any small displacement leads to a more stable product. So that's some sort of local maxima, and if you get a little bit to the left, to the right, you get some smaller Gibbs energy. An intermediate is the molecule that represents a localized energy minimum. I will show you an example so we will understand that. And when considering kinetics, the highest transition state is what matters, because you should somehow overcome that highest transition state, so it's probably the slowest part of the process to get over that state. And the step leading to the highest transition state is called the rate determining step. Okay. Here is an example, so let's disregard all these texts. Here is an interesting image. It shows you, here is basically energy, so this is Gibbs free energy G. This is so-called reaction coordinate. We'll get to that in a moment. That represents you, let's say, how the reaction goes. And here we have different states. So here is an initial state, so some starting materials, and they have some sort of, you can calculate somehow Gibbs free energy for them. Here you have products, you can calculate Gibbs free energy for them. But you don't go directly from starting materials to products. Your chemicals may need to go through some sort of intermediate states. And these states will have some highest point. If you, let's say, calculate the Gibbs free energy for each of that states, you can draw some sort of curve, and you will have a highest transition state that is basically this one. And you see that difference between initial and final products shows you that the reaction is spontaneous. So this delta G is less than 0, so it wants to go there. But to get there, you should somehow to overcome this peak. And basically how high is this peak determines how quickly will go your reaction. So basically kinetics is determined by this peak. I will not go through all that equations. Here is some more concrete example. So here is the dissociation of the 8 hydrochloric acid. So here are some starting materials. Here we have some sort of transition state. So this bond is not fully created, while this bond is not fully broken. So it's some sort of transition state. I don't think you can see that somewhere or extract this sort of thing. It's not a chemical, it's really a transition state. And here are the products. And if you calculate all that delta G's, you will get some picture like this one. So this is a transition state that you should overcome. And this delta G with double dagger will basically characterize you how quick the reaction goes, because your molecules should have enough energy to overcome that. And reminding you of the first slide where we had the Maxwell-Boltzmann distribution, you might guess that not all molecules have enough energy to surpass that state. So here is some sort of distribution for energies, let's say, and only some part may have enough energy to get through that state. Good. Here are some more examples of more reactions. So here is one of the reactions when we are attacking the carbonyl group, and we are attacking, that's basically a nucleophilic attack. And here you see the tetrahedral intermediate and what I showed you in the lecture number 4. So here we can write some sort of reaction rate. This rate is basically based on the so-called rate determining step, this one. But what's interesting, that's basically this sort of diagram. So we have extent of the reaction. Here we have starting materials. They have some Gibbs free energy. Here is our intermediate. So remember, transition state is some sort of local peak. So anything changes, you go down. Intermediate is a local minimum. So you see, this is a local minimum. So this sort of tetrahedral intermediate, it may even exist for long enough time so that we can even detect that. Well, not in all cases, but in some cases we can even detect that sort of intermediate. And here you see, to get to this intermediate, we should go through some peak, so through some sort of transition state when this bond is not fully created, while this electron is, I don't know, maybe, well, this double bond is not fully, let's say, broken or transformed into a single bond. So this is sort of transition state. Then we have this intermediate. Then from this intermediate we may go to the final products. And of course there is one more state that we should overcome. What we are interested in, well, the state that has the highest delta between this state and where we started, because that defines us some sort of minimum of energy that our molecules should have to overcome that and for the reaction to proceed. And that basically defines how many molecules can undergo reaction, which basically defines how quick the reaction is, so kinetics of our reaction. Here's another example. So here we have another rate determining step. So leaving group just leaves. So first order reaction. And once again we have a nice picture here. So here it is, we have starting materials. We have some intermediate step, this one. To get there we should go through some sort of transition state. We get here. From this intermediate we may go to another intermediate, pretty possible, through another sort of transition state, but not so high. And from this intermediate we can go to products. This is delta G for the overall reaction, so it tells us that the reaction is spontaneous, but it may take a really long time to get there, just because we need to go through a very high energetic transition state. That's why basically if you have, I don't know, some wooden chairs, they do not spontaneously combust. So yes, they have some sort of carbon in them, and it is energetically favorable to transform into carbon dioxide. But they are doing this pretty slowly, just because this transition state is very high, so they cannot overcome that transition state. So that's what happened. And if you calculate all that sort of coefficients, you will get that it's really it will take really long time. Okay, let me check where we are just for the moment. Okay, great. I will maybe show you just one or two things, and that will be really good, and there will be a really good point to stop. Here is just an example how can you manipulate all these things. So here is a manipulation with the help of the solvent. So when we are dissolving chemicals in different solvents, we can change their sort of energy, gives energy with the salvation energy, so they can go up or down. And here is an example that using a porothic solvent you can get your initial components up, so the intermediate state that does not get so much, let's say, that is not so much affected by the solvent, cannot get higher at the same amount, that you have lower transition. So this delta G is not so high, so you can get some better kinetics of your reaction. Here is an example of kinetics versus thermodynamic control. You have, in this case, you have kinetic products. These are the products that are easier to achieve because transition state here is lower. And you have thermodynamic products that have overall lower Gibbs free energy here on the product, but it may be more complicated to get there through this transition state. And basically, some points to notice that thermodynamic product, it has lower energy, so if you wait long enough, the chemicals will tend to transform into the thermodynamic product. When you just start reaction, they tend to transform into the kinetic product. So depending on of what you want, kinetic product or thermodynamic product, you may adjust the time that you spend on your reaction. So you either make it quickly or you wait for a long time. Moreover, at low temperatures, kinetic products are favored because the amount of molecules that have enough energy to overcome the transition state is smaller. If the temperature is higher, you have more molecules that can overcome the transition state, so you will get your thermodynamic product a little bit quicker. So you can use temperature to basically adjust between these two products. One more example, some sort of E-alkene and Z-alkene. Here you see this sort of reaction. It's performed on alumina surface. Well, let's disregard the details. I want you to see this sort of nice plot. You see here an intermediate, and from this intermediate you can go both directions, to the left or to the right, and you have Z-alkene on the right and E-alkene on the left. And E-alkene is basically produced as the first step when you overcome this sort of transition state. What it gives us, if we measure the concentration of E-alkene and D-alkene, we will get this sort of plot. So first a lot of E-alkene is produced, then if you wait long enough, the amount of E-alkene goes down, the amount of Z-alkene goes up. And that's basically what you can see from these plots and from this mechanism of the reaction. So you see that mechanism is so that it always creates only E-alkene, but then in the solution you can have this sort of intermediate formed, and from this intermediate you can go right, you can go left, and basically you end up with the thermodynamic product, so not kinetic product. Good. Basically I told you everything I wanted for today. I'm not sure if I'll be showing this to you tomorrow. These are, I guess you can look that at home, and tomorrow we will start with enzyme kinetics. These are just the mechanisms of the reactions, but now you have all these nice plots with the intermediate, with the different transition states, intermediate states, and you can just look them up and basically connect the dots from the lecture number 4 and this lecture. So here I have added all the mechanisms, and you see that they look sometimes pretty nice. So you have few, you have transition state 1 to 3, you have few intermediates, and so on. Okay. Okay, I guess with that being said, we can end